Okay, everyone, welcome back to this week's algebraic graph theory. And we have Chris Godsil today, and he's going to talk about Laplacian states. Chris, you can start whenever you are ready.
Yeah, thanks, Tina. I should point out I wasn't the first choice for this week. Originally, the plan was to have Sebi Choba give a talk, but he went off for a weekend skiing. He's been off for a weekend skiing with his family. He wasn't sure he could get back in time, so he was off the list. So then they asked Gabriel, but Gabriel was going to Rio for a weekend or so, so he's off the list. But I don't have a social life, so here I am. So we're going to talk about Laplacian states. Now, I'm talking about continuous quantum walks, and so I'm going to give a two-frame review of continuous quantum walks. So a continuous quantum walk, you have basically working two sets of things. You've got states, which are given by matrices, and you've got some transition operators, which are given by a family of unitary matrices. So they depend on time, U of t. Now, what happens if the walk, the way it's set up is if you start with, if the state of the system is D, then at time t, the state is given by ut d u minus t. Okay, so that tells you how the states change. Now, what's the matrix D? The density matrix, it's required to be posi-semi-definite, and it's required to have trace one. And actually, as the talk goes on, you'll see I get sloppy about the trace one part, but the posi-semi-definite matters. So, posi-semi-definite matrix with trace one determines a state for a quantum system. If the matrix is n by n, it's an n-dimensional system. Okay, and so the states are described by density matrices. I'll do some examples shortly. The U of t for everything we're doing today is going to be x of it times h, where h is some Hermitian matrix. Okay, in practice, A is going to be some form of adjacency matrix or Laplacian matrix today. In fact, normally be a Laplacian matrix, but the only requirement to make things work is H be Hermitian. Okay, so you have the Hermitian matrix usually going from a graph, and we have density matrices, and the two things combine to give us a continuous quantum walk. Okay, now so examples of density matrices. The simplest case is just to take the matrix with a 1 in the ith position and 0 everywhere else. That's posi-semi-definite, its trace is 1. And that's the case if you've seen quantum walks described, that is effectively the case you'd normally be working with. Now, I'm going to refer to these as vertex states because they're the vertices of the graph, you like, are 1 through n, and so each vertex determines a state called a vertex state. Now, you can generalize a bit. There's nothing stopping you taking a sum of vertex states. And see, I'm already sinning here because D doesn't have trace 1, but it is posi-semi-definite. And if I divide by the size of S, then it's actually a density matrix. But for most calculations, it's not going to matter too much. So I'll be sloppy about that. So there are two examples. As I said, nearly all the work has been done in this case. There's a little bit done where S has got size 2 in the context of fractional revival. And Bill Martin, his student who talked about so-called group state transfer, where they look at a more general setup. But these, okay, so they're the two common ones. The ones I want to work with today are of this form. So the point about here, D is vector times vector transpose. So that's a posi-semi-definite matrix. I've still got the trace wrong, but we could scale but divide by 2 and get an official density matrix. I'm going to call this a pair state. Now, we'll come back to why I might want to do that, but the point is it is well defined. So these are all states we could use for quantum walks. Now the Hamiltonians, the only Hamiltonians I'm going to use today, well, there's the Laplacian, the degrees minus the adjacency matrix, and the degrees plus the adjacency matrix, which is called the unsigned Laplacian or signless Laplacian. There are other possibilities. You can take any linear combination of A and delta, and these can all be realized easily in physics. There's more problems if you want to do something like the normalized Laplacian, but all these can be essentially implemented with the same technology. The first papers on quantum walks were actually referred to Laplacian, but they fairly quickly moved over to the adjacency matrix for no clear reason I could see, but that's, well, it doesn't make too much difference. It's the long and short of it. Especially if your graph is regular, of course, then these three things all give you the same behavior. So in that case, There's nothing to worry about. So okay, so I've told you what a quantum walk is in a very concise form. I've given examples of the states and the Hamiltonians. We'll be using the delta minus A, so x by t times delta minus A will be our transition matrix. So what's the problem we're given, this normal setup is you're given two states D1 and D2, and ask, is there a time t such that at time t, D1 has been transformed into D2. And to just remind you, D2 would be ut D1, u minus t. So the question is, can you choose, given D1, can you choose t so that D2 is equal to this? So that's, so this would be state transfer. Now, so it's a reasonably, from this point of view, it's actually a fairly simple question mathematically. You've got a family of unitary matrices we define by exponentials. That's not too bad, and you're asking this question. So it's a question about the unitary group in some sense. The other comment I want to make here, and it's important as you'll see in a second, in practice, the states that the physicists want to use are real. Now, this is not a requirement, and it's easy enough to write down states which are quasi-semidefinite, have trace 1 and aren't real. But in practice, the states that the physicists want to use in their quantum walks are real. And it turns out that this makes a big difference to the calculations in the theory, and I'm going to demonstrate that right now. To do that, I need to just explain the notation for the spectral decomposition. So I'm going to be using L for the Laplacian matrix. Okay, and so it's a real symmetric matrix, so we can write it as linear combination, eigenvalues times spectral idempotence projections onto eigenspaces. Since this is a Laplacian, one of these theta r's is 0, and they're all non-negative, but that's not going to cause any issues at all. Now, because this is the spectral decomposition, u of t is a function of L, and so we can evaluate it by applying that function to the eigenvalues, and so we get that the transition matrix u of t is just EDIT theta r times E sub r. Okay, and so if you can compute the idempotence and you've got the eigenvalues, and then you can compute u of t. Now we're trying to transform, asking, can I get D1 to D2? Well, in that case, we can write down a formula for D2 in terms of D1. And so we just multiply on the left by D1 on the left by u of t on the right by u of minus t, and substitute this. And after a minor calculation, you get this. So you get that the D2 is given by this exponential, which is a complex number of norm 1, times this product of matrices. Now, this is not a spectral decomposition. These are not the eigenvalues of D2. D2 is a Hermitian matrix. Its eigenvalues are real. Okay, but we have this expression relating D2 to D1. Now, the thing to notice is that because our Laplacian is a real matrix, the spectral and the eigenvalues are real, but spectral idempotents are real. So there are 4 matrices inside on that line, and each of those matrices is real. Now, what I'm going to do, if I multiply this on the left by EK and on the right by EL, I get this equation. So I get that EK D2 EL is equal to just a complex scalar times EK D1 EL. Now, there's 2 matrix products there, and they're products of real matrices. They're both real. And so that implies that that exponential there, e to the IT theta k minus theta L, is real. And anyway, it can be relatively plus or minus 1. Now, this is a very strong condition, and this leads to the constraints on that. You prove the eigenvalues are integers or quadratic integers and things like this, but we won't be worrying about that today. But so the point is that at time t, the EDI, these terms are all plus or minus 1. So at time t, they're all 1. Sorry, at time 2t, they're all 1. And so that says if I get transferred from D1 to D2 at time t, then at 2t, I get transferred from D1 back to itself. Now, in that case, we say that D1 is a periodic state. So if you have state transfer between 2 real states, then at time t, then the 2 states themselves are periodic at time 2t. Now, this is not too important physically, but it's very useful if you're trying to decide whether there's you can get state transfer because you can first go and look for periodicity, and periodicity is a little bit simple to work with. So periodicity is useful. The other consequence of this is if you look at the case where K is equal to L, you get that these expressions are equal. Now, it's not clear what intuitive meaning those products have, but they're equal for all K. And if that holds for D1 and D2, we say that D1 and D2 are strongly cospectral relative to the Laplacian. Now, some of you have seen strongly cospectral in other contexts, and this is equivalent to the usual definition, extends the usual definition. Okay, so that's probably all I need to say about that. I won't be discussing strongly cospectral vertices as we go on. And so, well, here's the statement that I went over before. If there's transfer from D1, real states D1 to D2 at time t, then D1 and D2 are both periodic at time 2t. Okay, and so that's often going to work with. So that's equivalent to saying that D1 and U of 2t commute. Now, this sort of thing is extremely important algebraically. This is surprising how much linear algebra reduces to deciding whether two things commute. So, for example, a matrix commutes with a projection onto a subspace if and only if it fixes the subspace in the complement. But we won't be aware of that day. So as consequences of state transfer, we get periodicity, we get strong cospectrality, and we get this commutativity properties. Okay, so so that's the background. So now we want to talk about Laplacian walks. And I need to say here, everything that I say here on Laplacians is joint work with Tina. She did a master's thesis on this, and we have a paper on the archive. So I just want to now, so the point about, I'll look at the Laplacian of K2, 1 minus 1 minus 1, 1. That's it, exactly this, what I was calling the state sigma 1, 2. So, I mean, the Laplacian is a quasi-semidefinite matrix, and so half this is a density matrix. Now, the Laplacian of the X itself is a sum of the Laplacians of its edges. Okay, that's straightforward enough. Now, so we've been interested in continuous walks on Laplacians, and people have looked at walks using vertex states, but it occurred to me, given that we have all these pair states in our face, what about looking at transfer between pair states? And the question we started with is that we have a graph, we've got two edges, E and F, and we're asking, can I get Laplacian transfer from the edge state from the pair state corresponding to E to the pair state corresponding to F? So this seemed a natural extension of the previous work. And so that's what I'm going to be talking about for the rest of the morning. Well, here's an example. If we use the path, take the path on 3 vertices as a Hamiltonian, then you can work out the spectral decomposition of P3. This takes a little bit of time. It's a good starting exercise. And so then you can work out an expression for U of t in terms of, well, path on 3 vertices. Well, actually, I don't know what the argument is. Laplacian path on 3 vertices are. But once you discover it, you get the spectral decomposition, and you discover at time pi on 2 that U of pi on 2 is equal to this little expression. So what matters here, it's a constant times J minus 3 times this backward permutation matrix. Now, if you've worked with Vertex state transfer, you've seen this matrix up before. It's a I times a permutation matrix that's going to swap the 2 vertices degree 1 on the path. Okay. Now, what if we take our initial state to be just the edge 1, 2? Okay, so there's it. That's the density, and I've been precise just this once. Now, the thing to notice is that the dj and jd are both 0. So j and d commute. So when I expand this mess, well, I've got this expands into 2 terms here, and this expands into 2 terms here. So there are 4 terms, but 3 of them have a d times a j in it. So the only term, there's only one term that matters, and that's this term. And so there's probably a -1 missing here, but so what you discover is that no, there's not. U of t at time pi on 2, d gets sent to this. So the pair state corresponding to the edge 1, 2 has been moved to the pair state corresponding to the edge 2, 3. So this is what I'm calling an example of what we call edge state transfer relative to the Laplacian. So it does happen. Okay, so we're not, that's not too surprising, but still you want to have an example. Now, the Qiuting worked on this for a master's thesis, and we were looking at transfer between edges, and at some point it occurred to us, well, we're really looking at transfer between pair states, and if we start with a pair state corresponding to an edge, and we get transferred to a second pair state, does that pair state have to be an edge? And we tried for a bit and we couldn't prove there had to be. And so you ask the question, why just pairs? Well, actually, so that's comment number one. The other comment here is, all that matters as far as the walks are concerned is that the states we're working with be given by positive semi-definite matrices. And, well, the Laplacian of K2 is a positive semi-definite matrix, but the Laplacian of any graph is positive semi-definite. So we can ask ourselves, is there any, we look at the situation, just pick some subgraph of X. And take it, it's Laplacian, it's a positive semi-definite matrix. So now you can ask for transfer between two subgraphs. Now, as far as the theory is concerned, this is going to work just the same as the edges, because this is why I did that calculation with the D1 and D2 and the strong gauge spectral and stuff. At no point there was I assuming that I was dealing with a pair state or a subset state. I just assumed I was dealing with a real density matrix. So long as I stay real, I get the same properties. I get the same ratio condition. Okay, I get the same restrictions on the eigenvalues. Everything is going to work. Okay, so it gets a little bit harder to work with what strong gauge spectral means, but by and large, everything works because all we needed to make these basic results work is for the states to be real. And so to be precise, so if we have some graph Y and the same vertex set as X, then we can write down as Laplacian, and that's it, and take that to be our density. So the Laplacian is appearing twice. We're using to construct the states, and we're also using our Laplacian as a Hamiltonian. Okay, we're free to do that. And so now, instead of just transfer from one pair state to another, we can transfer from one subgraph to another. Now, I should say, well, Tina and I, and more Tina than me, look carefully at transfer between edges and related things. With this more general concept, we haven't investigated computationally at all. Now, what can we deduce from this? There's one thing which, other things are interesting. If we do get transfer from the density corresponding to graph Y1 to the graph Y2, we have this equation. That tells us that Y1 and Y2 are Laplacian cospectral. I've got the similarity there. Okay, so this is a necessary condition. If you're going to get transferred from one Laplacian state to the other, they have to be cospectral. The other point is that since U of t is exponential of it times L, it commutes with L of x. And so U of t Lx, if I take x itself to be the initial state, then there's no change. Okay, so that tells us that ut and Lx commute, and it follows from this that these two matrices, Lx minus Ly, Y1, and Lx minus Y2, are also cospectral. So just think about the edge state for a minute. If I have two edges, they're K2s, they're isomorphic, they're clearly cospectral. And so the first condition, that the states be cospectral, is irrelevant. The second condition says that the edge-pleated subgraphs are Laplacian cospectral. Okay, and so that's that's a strong condition, and so we yeah, I'll leave it at that. Now, a related comment here. Well, Tina did some computations, and so what we've got here is a table for n through 5 through 8. here we have the number of connector graphs on n vertices. And using the Laplacian Hamiltonian, here are the number of graphs on 5 to 8 vertices with vertex perfect state transfer. So you get transfer from the one vertex state to another using the Laplacian as your Hamiltonian. And here's the corresponding figures for pair state transfer. And so it's clear, well, this is a limited amount of data, but it seems to indicate that, well, at least on small sizes, there's a lot more pair state transfer going on than there is vertex state transfer. And so this could justify the decision to actually look at what's going on in these cases. So, and again, this shows we have lots of examples of pair state transfer. Now, there's one nice thing about working with Laplacian is it works, it plays much more nicely with complements. And so the statement here is that if you have transfer from y1 to y2 with the graph x as the, or the Laplacian of x as the Hamiltonian, then you also get transfer at the same time using the Laplacian of the complement of x. Okay, so that sort of basically says if you have one example of pair state transfer of Laplacian and you take complements, you get a second. And here I've sketched the proof. The really only important thing to notice is that the Laplacian of the complement of x is given by this. Ni minus j is just the Laplacian of the complete graph. And so the Laplacian complement is just the Laplacian complete graph, take away the Laplacian of x. And so the other point is that there are 3 matrices here, I, j, and L of x, and any 2 of those commute. Because L of x times j is 0 and j times L of x is 0. So each of those commute. So that means that the transition matrix U of t factors into 3 terms. First term is an EDI NT corresponding to the identity matrix. This is an x with minus ITJ corresponding to this guy, and we get UL of minus t corresponding to this. Okay, and then we do a little bit of calculation to get that the x with minus ITJ is equal to this. Okay, now and then we remember that JD and DJ are both 0. So when you do the calculations, you discover that the UL bar D UL bar minus T is equal to UL minus T D ULT. So that gives us the result of our claim. So we can get complements for free. One consequence of this is that we can use joins to construct new examples. If we have some graphs, y1 and y2, and we get transfer on those, then we can often take joins, but I won't go into that. The other point, which I hinted at before and I want to go into now, is, as I said, after an embarrassing long time, we decided to ask ourselves, could we get transfer from an edge state to something which wasn't an edge state? So they're both going to be things of the form EI minus EJ times EI minus EJ transpose. But in the first case, we assume that IJ is an edge, and we're going to say KL, and KL not an edge. So could we get that transfer? It's a reasonable question, and you try to prove it. We didn't succeed in proving it. And then Tina came up with the following graph. So on this graph, you actually get transfer when you do the calculations from sigma 1,6, which is an edge state, to sigma 2,5, which is not an edge. So you have to widen your scope a bit. You can, if you choose to, say, I'm only going to consider transfer between edges, but you can get transfer from edges to non-edges. So now again, the point is that these 2 matrices, the density matrices, are similar. Okay, that's that's not a problem. So that means that when we subtract those matrices from the Laplacian, those matrices are similar. And so, and now this is okay. 1,6 is an edge in X, and so this is the Laplacian of X with 1,6 deleted. 2,5 is not an edge, so this matrix you've now got in the well, it is what it says there, and so essentially there's now a signed edge joining 2 and 5, and so these 2 matrices, or at least the adjacency matrices of these 2 things, are similar. Okay, now one way of thinking about this is that this guy, the Laplacian, is a sum of, it's a signed sum of matrices sigma ij for ij edges. You can think of this as this guy as being a signed sum. So a Laplacian is just a sum of Laplacians of K2s. But what's happening here is we're being forced to look at matrices which are sums of or signed sums of Laplacians of K2s. Now you've got to be a little careful here because sums of Laplacians of K2 are guaranteed to be quasi-semi-definite. These guys are not in general guaranteed to be quasi-semi-definite. This one must be because it's similar to this. Okay, so we're being forced to look at signed Laplacians with the sign who's got the property that the matrix is quasi-semi-definite. I have nothing useful to say about that, but it seems not that interesting. Now change direction a bit. So I'm going to work. There's a relation between these Laplacian walks and walks on line graphs. Now, one thing I noticed when preparing this talk, that I was really running out of letters to use, and then suddenly I get to this point. Now I want to talk about line graphs, and so I've got Laplacians of X and line graphs of X, and so there's too many L's around, but I think I've managed. So I want to work with instant matrices a little bit. So I've very carefully taken well, more precisely, instant matrices of orientations of graphs. So what I've drawn there in blue is an oriented complete graph on 4 vertices. And on the left here is the instance matrix of this orientation. So it's a signed matrix, each column contains a 1, a -1, everything else is 0. That's the instance matrix. Now, the key point is that if I take the instance matrix times its transpose, I get the degrees minus the adjacency matrix. So I get the Laplacian. So the Laplacian is quasi-semi-definite. This is, in some sense, the Sligut's proof. You can write it like this. Now, when you go the other direction, well, one thing, there's a theorem that says that if the products A, B, and BA are both defined, then the matrices A, B, and BA have the same non-zero eigenvalues with the same multiplicities. So they're connected in the wrong way. Now, we look at C transpose C. In that case, we're taking the entries of C transpose C. It's the ground matrix of the columns of C. Now, each column of C has got squared length 2, so you see 2's down the diagonal. And when you take the dot product of 2 different columns, you get a 0, a 1, or a -1. And so I very carefully worked it out, and that's quite probably correct. Okay, so you get a signed matrix. Now, the underlying unsigned matrix, if I left off the signs, would just be the line graph of K4. If you take the unsigned instance matrix, call it B, then B transpose B, B transpose B is 2i plus the adjacency matrix of the line graph. We're not getting a line graph here, we're getting a signed line graph. Oh, okay, it is what it is, and that's what we get. So let's go on a little bit. Now, so we have CC transpose is equal to Laplacian, and C transpose C is 2i plus written S for the assigned adjacency matrix of the line graph. Now, this is not an absolutely random signing of the line graph, but I'm not going to go that right now, but it's, it is some signed adjacency matrix. Now, from the point of view of quantum walks and things, I can use signed matrices as Hamiltonians just as well as I can use unsigned matrices. I just require them to be Hermitian. And from the point of view of physical implementations, I mean, generally speaking, the physicists don't want to vary the weights of the edges. It's too much trouble, but you can imagine situations where you could have some things with weight 1 and some with weight -1. So it's not a huge change. But I have those 2 relations. Now, from that, I get 2 consequences. If I take L, the Laplacian, times C, I get C transpose C. So that C transpose C is 2i plus S. So you get this relation. LC is C times 2i plus S. And taking transpose, for example, you get C transpose L equals 2i plus S times C transpose. So we have those 2 relations. Now, So now I'm going to do the obvious, and my transition matrices have been x by TL, but there's nothing stopping me to take x by t 2i plus s as my transition matrix. And so I'll get two transition matrices, and you discover that, that u of t, u sub L of t applied to C is equal to C times I've written u sub S of t, because I'm not going to write 2i plus s as a subscript all the time. But so just bear that in mind here. So we're using the skew adjacency matrix, not the sign adjacency matrix. And if you take the transpose of this, you get these two equations. So we have these relations. Now, the consequence of this is, suppose we're sitting with our Laplacian, and at time tau, we get transfer from D1 to D2. Then I claim at the same time, you get transfer from this matrix to this matrix using S plus 2i as your homochrome. Now, notice that this matrix is clearly posi-semi-definite because D1 is posi-semi-definite, and so wrapping it by a C transpose in C doesn't lose that. It's not immediately obvious to me that these two matrices, clearly if we get transfer from D1 to D2, these are density matrices. It's not immediately obvious to me that these two matrices have the same trace, but that's a consequence of what's going on, okay? So, but in any case, so these are posi-semi-definite, and so we're getting state transfer on relative to Laplacian states down here, and here we're getting transfer relative to whatever these states are. Now, we're giving it the stuff in blue on the right is just a proof of this comment, but that doesn't require, there's no real surprises. So I won't go through it, but so transfer down here corresponds to transfer of some form up here. Okay, now conversely, if we get transfer between states relative to S plus 2i as a Hamiltonian, and then at the same time, we get transfer between these states. Now, to give an interesting example here, I mean, S plus 2i is just a weighted adjacency matrix of a graph. And traditionally, when you're working with continuous walk-on graphs, we just use vertex states. So there's no reason not to take D1 and T to be vertex states. But now, so then what do these guys correspond to? Well, vertex states in the line graph correspond to edges in the underlying graph. And so the summary will be if D is a subset state relative to the signed line graph, then this is a Laplacian state. So you have a correspondence between what's going on the signed line graph and what's going on the graph. Okay, now the final little wrinkle here is we've got this signing of the line graph. And okay, signings can be fun, but sometimes you'd like to get rid of them. Well, you can. Any symmetric signed adjacency matrix determines a double cover of the underlying graph. And here I'm just going to state the result. So if you have a signed adjacency matrix for the line graph of X that determines a double cover, now for the particular signing that we get from the orientations, this double cover is isomorphic to the line graph of the direct product of X and K2. And so you can, again, lift the walks from this using the signed line graph as your Hamiltonian to using the adjacency matrix of the line graph of X times K2. And so you're now just working with a plain old-fashioned symmetric 0-1 matrix, although your states are going to be a little more complicated. And so, okay, so that's the second part. So we have this sort of layering process. We can go from walks on the Laplacian to walks on the signed line graph to walks on the double cover or on the line graph of X times K2. Now, this is going well. Now, signed Laplacians are all very well. The unsigned Laplacian, if you think about it for a second, you realize it's going to work much the same. If B is the unsigned vertex edge inches matrix, then BB transpose is equal to this, the degrees plus the adjacency matrix. This is what I'm calling the unsigned Laplacian. Okay, so adding the degrees, they're taken away. Now, the B transpose B in this case is just 2i plus the adjacency matrix of the line graph. So we got two Hamiltonians here. We have the Hamiltonian for the signed line graph and the Hamiltonian corresponding to just the line graph. Okay, and again, since the this guy is just the sum of the unsigned Laplacians of K2s, and so everything we've said before goes through, and states are all real. There's one comment I should make here is that if the graph is bipartite, then the Laplacian and the unsigned Laplacian matrices are similar, and so you don't need to consider the unsigned Laplacian in that situation. But in general, they're different, of course. And so we have that relation. And so the other remark is, again, since this is the form BB transpose, this is quasi-semi-definite, as is this. And so we can use little scaled unsigned Laplacians to give us density matrices, and we get the same type of equations we had before with the density U of t for delta plus A and U of t for the adjacency matrix line graph. I'm seeing some t's there. So we get the same equations. And in this case, you discover that, which is not too surprising, that PST between vertices of the line graph corresponds to transfer between, or PST between edge states on the underlying graph. And I'm doing all this for what is essentially something like close to a bad pun. Now, if we have perfect state trans, I'm calling the EI plus EJ, EI minus plus EJ transpose, I'm calling that rho IJ. It's always risky using rho when I'm handwriting, but I think it'll be okay in place of our sigma. So this is sigma without the signs, okay. And so if I get transfer from one edge to another, then again, these two matrices must be similar. Okay, and the point is, even if I choose I and J to be an edge of X, it doesn't follow that K and L has to be an edge. Okay, and so in that case, what this is a signed sum of adjacency matrices to K2, and so this is my candidate for a signed unsigned Laplacian, just to confuse the issue. And just to finish off, the Tina's computations indicate that pair state transfer with the unsigned Laplacian is less common than with the usual Laplacian. It's a good question. What's driving this? I think it's partly because complements, the extra stuff you're seeing on small sizes arises from graphs which are joins of smaller graphs. And so it's possible, but if we throw away the things that are joins, that the Laplacian state transfer is rarer than appears from the figures. But we don't know, that's an open question. And that's where I'm going to stop. And I don't have any pictures of rear ends of animals today, sorry.
Thank you. Okay, so is there any question for Chris? Okay, Chris. Actually, I just wonder, like, when you consider their subgraph states, the Laplacian state, like, when you're thinking about like state transfer, do you put a like restriction on the size of your like subgraph state?
There's nothing in. It doesn't seem to be a need to. I mean, there's, the point is that the density matrix doesn't really have to be attached to a subgraph of X. It just needs to be attached to some graph on the same vertex set as X. I didn't do it that way because I think it's a little more confusing, but so given where we're coming from, it's natural to think of these things as being subgraphs, and that's probably an interesting case. But there's nothing
Yeah.
You construct your transition matrix using a certain Hamiltonian, and then you ask for transfer between certain states. And so a large part of what it's saying is we can choose those states to come from Laplacians or from signless Laplacians.
Okay.
But yeah, I mean, the real issue is that we haven't, this is all very much, work in progress. We haven't sat down and looked for actual examples to see what can actually happen, aside from the pair cases. I mean, but there are.
Okay.
I mean, one natural class of states to look at would be stars, which would be another version of vertex state transfer, like the edges on a vertex.
Yeah.